Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, minimize marathon distances. The problem is a bit easier if you already know the trick of how to figure out the maximum marathon distance among a set of n points. But if you don't know that trick, the problem becomes a bit tricky. I was not aware of that trick before the contest, so I ended up taking a complete different route. I was not able to code that approach fully within the contest, but after the contest, I also realized that observation, and that simplified the problem a lot. So, as always, I will be taking you to the entire journey of how to actually get to that observation from scratch. And if you stick till the end, you will be able to understand or learn a few new things from this video. So with that, let's get started. The problem states that you're given a zero indexed array points that represent some points on the 2D plane. Distance between 2 points is defined as their Manhattan distance. We have to return the minimum possible value for maximum distance between any 2 points by removing exactly 1 point. So let's say these are the array of points. We need to remove exactly 1 point among these 4 points such that the maximum Manhattan distance between any 2 points is minimum possible, right? So let's say you remove this point first. So you will be left with 3 points, 5, 15, 10, 2 and 4, 4. If you figure out the maximum Manhattan distance between any 2 points here, you will see the maximum distance will be between 5, 15 and 10, 2, which is equals to 18, right? 5 minus 15 modulus plus 15 minus 2 modulus. Now let's say you remove 5, 15 this time. So you will be remaining with 3, 10, 10, 2 and 4, 4. And if you figure out the maximum Manhattan distance between any two pair of points here, you will realize that the distance between 3, 10 and 10, 2 is maximum possible, and that is equals to 15. Now this time let's say you remove 10, 2 and again figure out the maximum possible Manhattan distance between any two pair of points, and you will realize the distance is between 3, 10 and 5, 15 and 4, 4, and that is equals to 12. And finally, let's say you remove 4, 4, you figure out the maximum Manhattan distance between any two pair of points among these 3 points, and you will realize the distance between 5, 15 and 10, 2 is maximum possible, which is equals to 18. So which of these is giving you the minimum possible maximum distance? The answer is the removal of third point. So you will remove this point, and if you remove this point, among the remaining point, the maximum Manhattan distance is 12, and hence 12 is the answer, right? I hope the problem statement is clear. Now, what is the brute force approach to solve brute force solution to approach this problem? We will simply simulate whatever is given in the problem statement. We will try to remove this point, figure out the maximum Manhattan distance between the remaining points. Then we will try to remove this point, figure out the maximum Manhattan distance between the remaining points, and so on and so forth. So let's assume that you have a function pair with max Manhattan distance that takes in an array and will return you what is the maximum Manhattan distance. So what you're doing, you are calling this function n times, one after removing each element, right? So you are calling above function n number of times. So overall complexity of this approach would be n into c, where c is the complexity of this function, right? Now what will be the value of c? Assume that c, you implement this function in the best possible manner, that is, you just iterated over this array once without doing any fancy operations, and you are able to figure out the pair with maximum Manhattan distance. So the best possible complexity of this function would be order n. Now whether it is possible or not, that's a different question, but even if we consider best possible complexity, this solution will be of order n square, right? Again, this is under the assumption that c has the best possible value, but even n square is not sufficient because n is a 10 power 5. So we have to optimize this. That is, we can't even afford removing every point one by one and then checking what is the maximum Manhattan distance after each removal, right? So we have to somehow optimize that part first. So assume that you have figured out the maximum or the best point for each of the points in the array, right? So in other words, for 310 you figured out that 10 2 is the one which has the maximum distance from 310, which is 15. Similarly for 515 you figured out 10 2 is the one which has a maximum distance, which is 18, and so on and so forth. Now you have to reduce your maximum distance. Current maximum distance is 18, right? Now if you have to reduce your distance from 18, it indirectly means that you must have to remove either 5 10 or 10 2. If you don't remove any of these two points will exist in your final array, and if these 2 points will exist, 18 will be your answer, right? So if you want to reduce this 18, you must have to remove either this or this. So notice now you're not required to remove every element one by one. Instead, you have now reduced your search space to just 2 elements. So you will say either I will remove this point or I will remove this point. Whichever will give me the best result, that will be my answer. So the complexity of this approach would be now 2 into C, right? Which is directly dependent on how fast you can compute this thing, right? So just to like make it concrete, what you will do, you will first figure out, you will first remove 10 comma 2 and then you will remove 5 comma 15, figure out the maximum Manhattan distance, and whichever is minimum, that will be your answer. So if you remove 10 comma 2, this is the maximum Manhattan distance possible between any two pair of point. If you remove 5 comma 15, the maximum possible distance between any two pair of point is 15. Now because you want the maximum distance to be minimum possible, you will simply remove 10 comma 2 from your array, and the answer in this scenario would be 12, right? So hope this entire approach makes sense. Now what is remaining in this solution? Remaining thing is to figure out this mapping efficiently. In other words, we need, for each point we need to figure out what is the point to which it will give the maximum value, right? So for that you can see that okay, first of all, like what's the brute force way to approach that problem? So you have to figure out the best point for each of the points, right? Brute force way would be, start for this point you will try out every possible point, whichever will give you the best value, that will be your mapping. Similarly for the next point you will try out every other possible point, whichever gives the best value, that will be your mapping, and so on and so forth. So for each point you are trying out every other point, and the overall complexity would be order n square, right? So this is also not optimal because you will be doing this order n square operation twice, right? So we have to optimize this as well. That is, we now need to somehow figure out this best pair in less than order n square time. Now can you do this? The answer is, if you have I and j mixed, no matter what you do, you will not be able to do this get this mapping efficiently in less than order n square time, because to even compute the distance you need both I and j, and if you need both I and j, you have to iterate over all the i's and all the j's, right? So you can't get up, or you can't compute this entire thing in less than order n square time if you have both I and j combined. So we now need to think of how we can separate I from j completely, and then for a single I independently figure out what is the best j, right? That's the basic approach we are trying to take. So let's now separate I from j, and how to do that? We can simply expand this modulus. This modulus operation will become xi minus xj if xi is greater than or equals to xj, and this will become yi minus yj if yi is greater than or equals to yj. Similarly, this will become yj minus yi if it is reverse, right? and in the same fashion this will become xj minus xi if it is reversed. So there are 4 conditions and there are 4 possible expansion. For each of this after each of this expansion, you can just club the terms of I and the terms of j. So this will become xi plus yi minus xj plus yj. Similarly, this will become xi minus yi and this will become xj minus yj, and so on and so forth. Now, what will be your approach? Your approach would be, I will figure out the best j with this constraint, the best j with this constraint, best j for this constraint, and the best j for this constraint. Once I figure out the best j in each of these criteria, I can combine all of them to get the final best j, right? That's basically the approach. And for each of these, you can now speed up the computation of j. Or let's say you have this I, you want to figure out the best j in this format, right? So what does this mean? This means that your whatever your j would be, the value of x for that should be less than equals to the value of x for the ith element. So if you have sorted this entire array, let's say with x coordinates, you are only interested in these 2 elements, right? Now among these 2 elements also, you are only interested in the ones that has yi greater than equals to yj. Now for these elements, what you want the one which has the minimum value of xj plus yj. So you among these 2, you want the one which has the minimum value of xj plus yj, and that you can figure out easily using any data structure that is sorted in nature. So let's take an array of 5 different points. You want to figure out the best possible point for each of these, and you have sorted this entire thing with respect to x first. So the first point is 3 comma 10, then 4 comma 4, and then 5 comma 15, then 7 comma 9, and finally 10 comma 2, right? Now let's say you are trying to figure out the best possible j for this I, and whatever complexity you will get, let's say you are able to figure out the best possible j in order x time. So the complexity of figuring out the best possible j for all the I would be order n into x, right? So we need to make x either log n or 1, right? So that's what our goal is. Now if you look at it here, for this I, you first need to figure out the best possible j in this format, then you will figure out the best possible j in this format, then this one, and then the last one, and finally you will club them all up to get the best possible j across all the formats, right? So let's talk about the first one, where xi is greater than equals to xj, right? So you only want to take j's which are for which xj is smaller than equals to xi. So in other words, you are only interested in smaller points, right? Now second thing is yi is greater than equals to yj. In other words, for this point, like you only want to consider among these 2 points, you only want to consider those points for which y value is also smaller. So y value is 15 and these 2 has smaller y values only, so you want to consider these 2 points. Now among these 2 points, which one you will take? You want to maximize this value, right? So if you want to maximize this value, this thing should be minimum possible. So among the possible j's, you want to take the one which has the minimum value of xj plus yj. So we have already calculated the value of x plus y. So minimum value of xj plus yj is at j equals to 1. The best possible j for this I would be 1. That is, with j equals to 1, this I will give the maximum possible distance in this format. Similarly, you will get some j for this format and some j for this format, and you will simply club them all up to get the final answer, right? Now what is the operations you are doing to figure out this j? Now firstly, you are you want to figure out, you only want to consider those j's for which x value is smaller. That is, at any given point of time, you will either be looking at everything to the left of y or everything to the right of y, because it is sorted with respect to x-axis, right? So that is good. Now you also want to check whether yi is greater than equals to yj. Now that becomes interesting because there is no particular order with respect to y here, right? So you can't simply do a binary search, or you can't simply have a range in which you can figure out what is the minimum value or maximum value of this x plus y. So because the y is not sorted in any particular order, because y is not sorted in any particular order, this you can't do with the range query. Like minimum value of xj plus yj, you can't figure out using range query. And to actually make it range query, like if you do it naively, that will take you order n time, right? You will simply go over every y, see which one is satisfying this condition, and for this y you will take the x plus y value. So that will take you order n time, which is something we can't afford for a single I. Otherwise it will be order n square for all the indexes. So we have to somehow not iterate over all the possible j's here, and for that you can do something like merge sort tree, because what you want is you want to sort in second dimension. You already have sorted this entire structure with respect to x. Now you want to sort in second dimension such that you can have a range query over there. So that you can do in using merge sort tree, and this entire question of what is the minimum value of xj plus yj for this range is something you can answer using a variation of merge sort tree in order log square n, right? But that will be very complex. So if you are interested there, merge sort, like there is a complete video on merge sort tree in this channel, you can watch that particular thing. But it will be very complex, and that's where I would say I have done blundered. I went down this path and try coding it and was not able to complete it within the given time of the contest. So even though that's a valid solution, this is overkill. Why? Because if you make one small observation, this entire thing or this entire effort will go away. Notice that why you need merge sort tree, because you wanted to search for j in this particular range, but is that required? The answer is no. So let's say you take one j which doesn't satisfy this condition. So you wanted j such j for which xi is greater than equals to xj and yi is greater than equals to yj, but you took one j in which this condition is not satisfied. In this case you can say xi is smaller than xj, right? So this condition is not satisfied. So if you take any such criteria or any such j, the final value you will get will be smaller than what you will get from the valid j which satisfies this criteria. And why that is true? Because if you think xi is greater than equals to xj, what does this mean? This means that this thing is positive. Xi minus xj is positive. Similarly, yi is greater than equals to yj. What does that mean? This means that yi minus yj is also positive. So overall this value of this entire thing is positive. But if let's say this is less than, then xi minus xj will become negative. So the value will decrease, right? So any j which doesn't satisfy this criteria, automatically the value of this expression at that particular j will be smaller. So if you look closely here, what is the value of this expression at this j? Xi plus yi, which is 20, minus xj plus yj, which is 7 plus 9, 16. So the value at this particular j is 4. Now let's talk about the value at this particular j dash. Again, xi plus yi, which is 20, minus xj plus yj, which is 8. This is equals to 12. This is greater than what you have previously, right? So because by definition the value will be greater at a valid j, you don't need to consider, or you don't need to pick and choose j. You can simply say that, okay, for I want the maximum value of this expression across all j's, and I will be getting the maximum value only at j which satisfies this condition, but I don't need to constrain my search. I can search over the entire search space and get the best possible j. So in this case, what you will say, I want, like for this expression to be maximized, I want a j at which xj plus yj is minimum possible. So you will search in the entire array, obviously except this ith element, because this is what you are searching for. So in this entire array, what is the best possible j? Best possible j would be this one, because that has the minimum value of xj plus yj. So for this for this type of constraint, j equals to 1 will be the best possible j. Similarly for this one, you will do the exact same thing. You will say what is the best possible j such that xj minus yj is minimum possible. So xj minus yj is minimum possible at -7. Notice that -10 you will not do, because -10 is equals to I. So it is minimum possible at -7. So for this I, j equals to 0 will be the best j for this format. Again, best j mean that will give you the maximum Manhattan distance with I. So you will similarly you will figure out other two j's as well and take the j which gives you the maximum Manhattan distance. Now what is the overall time complexity here now? For each expression what you are doing, you are simply figuring out either the smallest value of xj plus yj, or the largest value of xj plus yj, or the smallest value of xj minus yj, or the largest value of xj minus yj. So you can simply maintain this smallest and the largest values of xj plus yj and xj minus yj with you, and each of these expression you can simply answer in just order one time. So overall you will be able to figure out these j's in order one time, and after you figure out all the 4j, you can combine them again in order in just 4 operations to get the final result. So overall the complexity of figuring out the best possible j for a single I is just order 1. So overall you can figure out the best possible j across all the i's in just order n time, right? So just to reiterate, what we have done is we have solved this particular function in just order n time, and this function will give you what is the best possible j for a single I. So this function will give you this exact map, and once you have this exact map, you will look at the one with the maximum distance, and now you will know which of them you need to remove, either 515 or 102. Now you will call the exact same function with first either removing 515 with the remaining elements, and then removing 102 with the remaining elements. So you will call the exact same function that will again take order n time, and this will also take order n time, and you will get this particular array, right? And whichever is the minimum, that is something you will return. So you will say the maximum across all of them is 12, maximum across all of them is 15, the minimum across 12 and 15 is 12, so 12 will be my answer. That is, after removing an element, the minimum Manhattan distance I can get for across all the remaining points will be 12, right? So hope this entire solution makes sense. So what you need to do, you simply need to code this function, and once you have coded this function, you can simply call this function thrice in this fashion to get your final result. Now what will be there inside the function? You will figure out the best possible xj plus yj and the best possible xj minus yj, and once you have these two values, you can simply, for each I, you can figure out what is the best possible j here, right? So overall complexity is simply order n. I am not showing you the code for this. I would encourage you to pause and try to code this entire thing by yourself. I will attach one solution or the code for this in the description down below. The code would be exactly what we have just discussed. If you have any doubts, feel free to post them in the comment section below. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.